I'd like to talk to you about conservative forces and energy. At this point in the unit, you understand that the work that is done on a system results in a transfer of energy. And that system energy changes precisely by the amount of work that is done. Go ahead and look at your College Board equation sheet. Now we have this change in total energy denoted with a delta capital E. And the change in total energy would be the changes in kinetic energy, in gravitational potential energy, in spring potential energy, thermal energy, etc. And that is all equal to the work. Now, a conservative force, such as the force of gravity or the force of a spring, changes the amount of potential energy that's in a system. And remember, potential energy is referring to gravitational potential energy, spring or elastic potential energy. So our conservative forces, force of gravity, force of a spring, can change this amount of potential energy. However, mechanical energy remains constant. So I'm throwing out a lot of different terms here, and I don't want you to become confused. Please recall from a previous video that mechanical energy is referring to the sum of both the potential and the kinetic energy. That is what I mean when I say mechanical energy. Furthermore, the work done by or against a conservative force is independent of the path taken. Now, what does that mean? Go ahead and look at this diagram. We have a man, and I want to look at this guy here first. And he is moving an object from points A up to point B, and that has a height of h. He's using a pulley system. And so he is literally moving this object vertically a distance h. Because he's doing work on a system. Now, what is the system here? The system is the object and the earth. So he's doing work on the system, and the system is going to be gaining gravitational potential energy because the object is going from point A to a given height above a referenced zero line. And in this case here, we can just call the zero line down at point A. Now, let's look at the man going up the stairs. Clearly, that's a longer path. However, the change in potential energy is identical to the man using the pulley system. When that object gets up those 3 flights of stairs to point B, it has gained precisely the amount of gravitational potential energy that was done by the pulley raising the object vertically. That is what is meant by independent of the path taken. Now, let's go ahead and look at another scenario with Stickman. Hey, Stickman. Stickman is now going to raise this block. Now, because he has raised the block, he's doing work. He is external to the block earth system. So he's doing work onto that system. And the system is gaining gravitational potential energy. It's gaining energy. Now look at the free body diagram here. Stickman applies an upward force. The earth applies a downward force onto the block. However, the block moves upward 0.5 meters. That means that this is positive work that's being done. That means that the block earth system is gaining gravitational potential energy. Now, if we look at our work equation, and we go ahead and look at the force here. And remember, it's a conservative force, and I'm referencing the downward force of the earth on the block, the force of gravity. is equal to the product of the mass times the acceleration due to gravity. If we plug that into our work equation and acknowledge that the angle between the force applied and between the displacement of the object is 0 degrees, cosine of 0 degrees is 1. That means that we get the fact that the energy is equal to mass gravity and the change in height. Well, the change in height for all practical purposes is this distance the object moves vertically. That is the gravitational potential energy in this system. Now, conservative forces never change the amount of mechanical energy in a system. And again, I said I was throwing these terms out. I need to expound on these so you don't become confused. Remember that mechanical energy is the sum of potential energy and kinetic energy. So the work done by a conservative force, again, force of gravity, force of a spring, is changed into kinetic energy. It must be if mechanical energy is conserved. So here we have an object that is 2 meters above a zero line. Now, this zero line that you see at the bottom of the screen, it is not the ground. It is an arbitrary line that I have chosen to place to teach you about how energy is converted from gravitational energy to kinetic energy. However, the total mechanical energy is conserved. So please keep that in mind. Mechanical energy, again, is equal to the sum, and these must stay constant. So potential energy and kinetic energy is constant. Therefore, we can state that our initial mechanical energy must be equal to our final mechanical energy. In other words, initial potential and initial kinetic must equal the final values for mechanical energy to be conserved. The object drops 2 meters. Now again, remember, it stopped on your screen, but the zero line is not the ground. So this object drops. Let's talk about the change in potential energy. Well, it was above the zero line, and now it is at the zero line. So we can calculate the change in potential energy very easily by plugging in values for the mass of the object, little g, and of course the change in height being 2 meters. Therefore, its change in potential energy is 20 joules. Now we can use this information to then find out what is happening to the kinetic energy, because as the potential energy is being converted into kinetic energy, the object is moving, okay? And we know kinetic energy to be 1/2 mv squared. So that's really what's occurring here. So let's look at kinetic energy must have changed by 20 joules, okay? If our initial potential energy was 20 joules, it was all converted into another form of mechanical energy. Well, that other form is kinetic energy. So yes, the crate is moving. So let's look at a next part of this scenario. The object's dropped. How fast is it moving at the zero line? Which again is not the ground. So we can say, well, 20 joules is equal to the kinetic energy 1/2 mv squared. We can then do a little bit of algebra, multiply both sides by 2 and divide by the mass of the object and take the square root of that quantity to get the speed of the object at our zero line. And it's moving approximately 6.3 meters per second. All of that potential energy was converted into kinetic energy. Let's look at a UAM alternative. Now, we know nothing about time, so the only UAM equation that makes sense to try to use would be the one you see on your screen. And because the object is dropped, that implies that our initial velocity was 0. Well, if the initial velocity is 0, we can simplify this equation. And we can now go ahead and plug in values. Remember, the acceleration is the acceleration due to gravity. So we can put in our 10 meters per second squared and our change in height, which is what the delta y is saying, a change in vertical position, which is 2 meters, and take the square root of that, and we get 6.3 meters per second. We get the exact same answer that we did using energy. Now, let's talk about a spring in the final part of this video, because the force of a spring is a conservative force, which means work done on or against this force would result in a change in mechanical energy. But mechanical energy is still conserved. So here we have a spring. You're given the K value to be 100 newtons per meter. Remember, K is a property of the spring. That's the spring constant. And that doesn't change unless you change out the spring. And it's compressed 30 centimeters on a frictionless surface. Find the potential energy of the spring block system. Okay. Well, we have our compressed spring here, and referencing your equation sheet, we know that the potential energy of a spring, or the elastic potential energy, is equal to 1/2 kx squared. Remember, the x is referencing the extension or compression of the spring. So we know that to be 30 centimeters. And of course, we'll convert that into meters so that we're in the base SI units for our calculation. We put these values in, we can find that the spring energy is 4.5 joules. So it has 4.5 joules of this potential energy. But what happens when the spring is released? That potential energy is going to be changed into kinetic energy. So now we're asked to calculate the speed of the 1 kilogram block when the spring is released. So at that instant, all of the spring energy is converted into kinetic energy. So right when the spring was first released, we want to know how fast the block was moving. Well, we know that the change in kinetic energy must be equal to the change in potential energy for mechanical energy to be conserved. So 4.5 joules is that change. And now we can set that equal to 1/2 mv squared. We can do a little bit of algebra here, and we can solve for the velocity of the block the instant the spring was released to be 3 meters per second. All right, guys, so we've talked now about conservative forces and energy. In the next video, we're going to talk about non-conservative forces and energy. And I'll see you guys in class.